So, okay, here it is. So, what I'm going to deal with and to tell you is in the area of computing with infinite data. This is also the title of this big project. And so infinite data, the prime example are real numbers. And when we look to scientific computation, to engineering, what do they compute with? Real numbers. But real numbers, as they are on the computer, are a problem because they don't compute with real numbers, they compute with floating point numbers, and they have rounding errors and so on. So we are dealing with another approach, and so this gives a bit of a flavor of the problems that occur in our approach. So let's assume we have two topological spaces, T and T dash, and they are T0 spaces. We will see why. And they have countable bases. And we assume that the bases come in this way as they are written, so they have indexings, and I will refer to these indices. Now, in this approach to this kind of computable math, we want to get many information where in normal mathematics the mathematicians only derive, oh, they exist. We want to get hold of the object that exists. We want to compute it. So first of all, we want to define when is a map effectively continuous. You know a map is continuous, globally continuous, if the inverse image of a basic open set is open. Now, here we say a map is effectively continuous if there is an enumeration procedure that, given this B dash I, enumerates a set of basic open sets in the domain space such that the inverse image of B dash I is just the union over this enumerated set. So that's the way we get hold of the inverse image. Now, I said T is a T0 space, so that means in particular that the points X are uniquely determined by the corresponding neighborhood filter, n of X. So that means a point is uniquely determined by all basic open sets that contain that point. Now assume when we are that we have a device such that if we are given a point X, then that device truly answers question of the form Bi is in the filter or not. In other words, Bi contains X or it does not contain X. So if we have this then, and we have this effectively continuous function, then given X, we can, and given this device, we can effectively produce a list, say B dash F0, B dash F1, and so on, of all basic open sets, such that f of X is contained in a basic open set, B dash N, in this list. How can we do this? Well, in parallel, we look to all basic open sets B dash I. Then we generate this list B0 or G of 0 and so on, which now depends on I. And then we use this device to find out if X is in one of this BG of N. And if so, then we know X must be in the inverse image of B dash Y, and then we can put B dash Y or B dash Y on this list. Okay, so we have a way, given X, to get hold in a computable way of the point f of X by just enumerating all basic open sets that contain him. And so we say that in this case the function is computable. Now when you think back in the first half of the last century, a big problem occurred to mathematics when Russell came up with his paradox. And just before this, Cantor had introduced a set theory, and everybody was quite happy with this, and so that much of mathematics could be written up in a uniform and exact way. And then there was a paradox, and people started to think, what will we have to do to get rid of the possibility such that there are such paradoxes. And one of these approaches was that we no longer want to use reasoning that is non-constructive. So constructive means that we really, when it means it is said there exists something, it's not sufficient just to do some kind of proof, but we really have to construct the object and to show that it has a property where we say there exists an X that has this property. And so what does it mean? Then there was a discussion among these people, what does it mean to be constructive? And Markov in Russia advocated to consider only objects that can be computed. So here constructive means it can be computed. And I decided to use the constructive, the word constructive here, because otherwise we have to always say computed, computed, computed. And so we say a point is constructive if there is a program listing all basic open sets that contain this point. So you see, Bn is in the neighborhood filter of X, or Bn contains X, exactly if n is in this list. And we have seen, because we have a T0 space, to get hold of a point, it's sufficient and necessary to know all the basic open sets that contain it. Now, programs are finite pieces of text, and therefore they itself can be manipulated by a program. So we can have programs that read in the code of another program, and then they do something with it. For instance, the compiler is such kind of program, and then the output is a program again. So we will assume that G is a program that determines such a unique point, determines in a unique way such a point with this property star. And these are the constructive points, and we contour, and say TC should be the set of all constructive points. And then Markov defined another way when a map now on the constructive points is computable. I call it now Markov computable. So in the following way. So suppose you have such a constructive point and it's determined by a program G. Then you want to have to know how can you determine capital G of xg. So what then the requirement is, there is a program. This program starts to manipulate G, and then the output is again a program which does such an enumeration as in star, and by that way determines a point in the range space. So you don't need to know any approximation of X. All you need to know is a finite program that generates an approximation, but you will not manipulate the generation, but you manipulate the program, and this gives you Markov computability. So we have seen that every computable map, and a computable meant in particular that the map has to be effectively continuous, that every such map, if we restrict it, then it is a restriction. If we restrict it to the constructive point, the restriction is Markov computable. That was what I mentioned in the beginning. And the continuity problem is now concerned with the converse implication. Is every Markov computable map on the constructive points the restriction of a computable map? And first of all, I would like to consider some special cases. So we start with the set of all partial maps on the national number. I always use this harpoon to denote the set of partial maps. And this set comes with a canonical topology. So in particular, a finite function, that means a function with a finite graph, is a partial map. And so for any such finite function, you take all those partial functions, the graph of which is a superset of the graph of f, and that defines a set, and the collection of all these sets defines a topology. It's a basis of a topology. That is the canonical topology on this on the set of all partial maps. Now, what are the constructive objects? So Church-Turing thesis tells us that the partial computable functions, as we deal with it in theoretical computer science, for instance, that are exactly the constructive objects in this space with respect to this topology. Now let P denote the set of all partial computable functions. Then the first result in this respect was by Mayel and Shepherdson, and they showed that indeed every Markov computable operator on P is a restriction of a computable operator on this space of all partial maps from n to n. So in that case, it was a positive answer to this question. The next space to consider in the area of computability was the set of all total computable functions. So in general, let n power n be the set of all total functions on the national numbers, and R be the total computable functions. Now n power n, also known as bare space, that comes equipped with the canonical metric. So of course, if f and g are two total functions and they're identical, then the distance has to be 0. Otherwise, there is some argument where they both differ, and we look for the smallest such argument, and then we say 2 to the minus the smallest argument. And then we consider those maps that are 0 almost everywhere. So very similar to the finite functions in the case of the partial maps. And we take then all total functions that have distance smaller than 2 to the minus n of such an f, and this gives us a collection of balls, and that is just the basis of the metric topology. And in that case, now Kreisel, Lacombe, and Schoenfeld, they showed again every Markov computable operator on R is the restriction of a computable operator on n power n. So again, a positive answer. And both results have been generated. Now I said that in the case of the partial maps, there is a natural partial order because this inclusion between the graphs. And in computer science, special partial orders have been of special importance, namely partial orders which are lattice-like, but only certain sets have least upper bounds, sets that are directed, and not like in a lattice, all sets have a least upper bound. And in that case, under some effectivity conditions, it was shown by many authors, just by considering different effectivity conditions, that again Markov computable operators between subspaces of constructive elements of such partial orders, they are known as domains, are restrictions of computable operators between the domains. In the other case, we have seen that the space of the total function is in particular a metric space, and again under some effectivity conditions it was shown independently by Zaitin in Russia and Moskovakis in the US that Markov computable operators between the subspaces of constructive elements of recursive metric spaces are restrictions of computable operators between these metric spaces. So we have positive answers, and the question is, well, everything looks fine. We have two types of topological spaces. They are indeed of very different kinds. So the domains are T0, but not even T1 in general. In the second case, we have a metric space, which is Hausdorff and more than Hausdorff. So, and the result holds in both cases. So that makes us very hopeful. But there is a result by Friedberg, which says there is a Markov computable operator from the total recursive computable function into the partial computable function that is not continuous, and hence not the restriction of a computable operator between the total functions and the partial functions on n. You remember, computable operators implied that they have to be effectively continuous. So the question is, which Markov computable maps are effectively continuous? Now, if one looks to the proofs, all the proofs I mentioned so far, they all follow a canonical pattern, which I want to explain next. So first of all, a general setting. We now consider only T0 spaces that are countable. That means we restrict all the spaces to its computable or constructive elements. Again, we have a countable basis, and where before we had, I said, oh, the constructive elements are those for which there is a program that does the generation of all basic elements that contain a certain point. Well, if we just encode this program by natural numbers, then we get a partial surjection of the natural numbers onto the space. And we have already assumed in the very beginning that with the basic open sets we have a total enumeration of them. Now I will define effectively continuous in a bit different way. Classically it's equivalent anyway. So we say a map is effectively continuous if it is effectively pointwise continuous at every point xi uniformly in I. So to understand what uniformly means, let me first say what it means to be effectively pointwise continuous. So we have a point y, and we want to define when f is effectively pointwise continuous at y. So the normal definition of pointwise continuous says, okay, given a b dash n, which contains the function value f of y, then there is a basic open set in the domain space that contains y and is included in the inverse image of bn dash. Now, effective means that we can compute the index of this basic open set, that we can really get hold of it. And uniformly means, so here we have, that means that we have a program that given m, given n, computes such an m. And here we mean that we have a general procedure that first takes in n, then gives out a program which does this job. Now, Beeson and co-authors have studied the possibility when the equivalence of when the continuity problem has a positive solution in various different settings, which all can be called constructive. And so here is shown that one cannot derive that Markov operators are pointwise continuous without Markov's principle. So to understand Markov's principle, think of a normal proof in mathematics that is an indirect proof. So you want to prove that alpha is a function, that the function has a 0n. So you assume it doesn't have a 0, and you derive a contradiction, and then you know that you have an n such that alpha of n is 0. Now you don't know anything about this n. However, if the function alpha is computable, you can do the following. By the classical result, there is an n. So you can search for it. You start to test alpha of 0, is it 0 or not, alpha of 1, and so on. You know by the classical proof there is an n. That means you cannot run to infinity without finding it. There is a stage when you come up with such an n, just by searching. So in this case we can also constructively assume that if we have that not there is an n alpha of n is 0, then there is really an n alpha of n is 0. And so that was for the in setting that we deal with computable mathematics. For the general case, you have to assume that this principle holds. So Beeson has shown you cannot do without this principle. So we have to assume, we have to start the proof in an indirect way. So given the point y, we have to assume that f is not continuous at y. So what does that mean? So we have given a basic open set b dash n, and we assume it contains the point f of y. And then we have to assume indirectly that for all bm containing y, that f of bm is not mapped into bn dash. Now here comes the critical point, because in order to derive the contradiction, we need that this statement f of m is not included in bn dash holds constructively. So classically this means that if it would hold, that if f of bm is included in bn dash if for all z in bm, f of z is included in bn dash. So the negation is there exists a z in bm such that f of z is not included in bn dash. And here we have to effectively find such this z. So we have to assume that this can be, that we can really find such a z which is not mapped, which is in bm but not mapped into bm dash. That is the essential point. And in all the, as you will see, in all the cases I mentioned before, one can do this, and the proofs I mentioned, they do that. They do so. So let us look to the first case. That is, T is a domain. I said the domain is in particular a partial order. So in that case, we have that every basic open set, remember the case of the partial functions, there we had the finite functions and all the map functions that are above it, so the graph of the function is above of the graph of the finite function. That holds in general for the basic open sets in domains. Now we can show that Markov computable maps are in particular monotone. And so assume that Z is mapped inside Bn dash. If that would be the case, then by monotonicity and by this property, all of Bm would be mapped inside, which is not the case by our assumption. So this Z is already a witness that which has to be outside Bn dash. So it's very easy in that case that we find our witness that we are looking for. Now let's look to the metric case. In the metric case, we have these balls, and we have that in the interior of the ball itself is completely enumerable. So we can search within this ball, but we can also search in the exterior. The problem is the boundary. And so what we know by the assumption is that first of all we have some Bn dash that contains this f of y, and we know that f of z is not in Bn dash. So it might be in the exterior, then we would be happy, but in the bad case it's just on the boundary, and then we cannot find it because we can only search inside and outside the ball. We cannot search on the boundary. So what do? We look for a smaller ball such that the closure of this ball is still included in Bn dash. So this is Bn dash with f of z on the boundary. So we find a smaller one, the closure of which is included in the open set Bn dash, and then we have that the complement of B dash a, that the complement of Bn dash is now included in the exterior of Ba dash. So we are happy because in the exterior we can search. So we can search for a point f of point z that is mapped in the exterior of Ba dash. So by this way we can also find the witness z we are looking for, and that is how it is done in the proofs. Now in the 80s there were two big approaches how to deal with the semantics of a programming language in a formal, mathematical, precise way. Before, when you look to a book on a programming language, then mostly you will find that the semantics, what the different constructions in the language mean, they are described with text, just in English words. And then it was found out that that leads to very different implementations. So you cannot move with your program from one compiler to the other compiler. The results may be different. And so people wanted to have a formal, a neat way to describe the semantics. And there were two main schools. There was Scott, he proposed domains, and there was the Bakker, he proposed metric spaces. And then Mike Smith said, okay, let's bring these two schools together by using quasi-metric space. Because metric spaces as well as domains, they are quasi-metric spaces. So what is a quasi-metric? A quasi-metric is more or less a metric, but it need not be symmetric. Which is not so bad, because think of the example, you have a point in a valley and a point on top. And you want to measure the distance not in kilometers but in energy, and then when you walk up the energy is much different from the energy you need to walk down. So it's not a bad concept. Now every quasi-metric defines a partial order in this way. So y is below z is the distance from y to z is 0. So we see that the point z that can be reached by no effort from y, that is a cone. It's no longer a point. And then you have that the quasi-metric is anti-monotone in the first and monotone in the second argument. And what is important, if we fix the first argument as a function of a second argument, it's continuous with respect to the metric topology on T and the lower topology on the non-negative rules. That is the topology which comes with intervals which are left closed and right open. The consequence is, so also with the quasi-metric, we define the topology by taking such balls, just as in the metric case. But the exterior of such a ball is not necessarily this ball, which is like it is in the metric case, because in the metric case we have that the metric is continuous with respect to the normal topology on the reals, and then this is open. But now this is not the case, so this is not necessarily the exterior of this set. Moreover, in the quasi-metric case, with every quasi-metric there is a conjugate quasi-metric, which we define by just swapping the two arguments around. And the nice thing is that the partial order with respect to the conjugate quasi-metric is just the inverse partial order of the quasi-metric. The balls which respect to the metric are upward closed under the partial order, just as in the domain case. And with respect to the conjugate metric, quasi-metric, these balls are downward closed. I mean, they are upward closed with respect to this partial order. That means they are downward closed with respect to the partial order defined by delta. So let's consider that T dash is a quasi-metric space. Now we need to find again a witness, which is in Bm, such that f of z is not in B delta dash n. And again, we need to be able to search in the complement of this set, just to find of this B delta dash n, just to find such a witness z. And again, the general philosophy is that only open sets are searchable. And again, we have the case that the witness may be contained in the boundary of B delta dash n. So in the metric case, what we did is we looked for a smaller basic open set in here, and then we knew that this complement was in the exterior of this smaller basic open sets. But as I said here, the exterior is not necessarily this set. So what I said, that is not true. In the quasi-metric case, the complement of this set is not necessarily contained in the exterior of a smaller basic open set. So we use both topologies. We proceed with the finding a smaller basic open set here, and what played the role of the exterior is now a basic open set with respect to the conjugate quasi-metric. So what we do is we search for, so we have our basic open set B dash n. We have f of z, which may be just on the boundary. then we search for a smaller basic open set with respect to delta, and for one with respect to delta star. Now the one is upwards closed and the other is downwards closed, and they have to be disjunct. And then we can do this, and then just by searching here in this downward closed set, we can find the point. So the essential point is that instead of using the exterior, we use another topology which is closely related to the given one, but which is downward closed. And in the setting of bi-topology, this property is just what is called bi-Hausdorff, because you cannot have Hausdorff property since with this kind of spaces, but you have a related topology, so that you have this possibility that any 2 points can be separated by one open set in the first topology and the other in the other topology. So that gives a hint how when we could generalize this to the to more general spaces. So as I said, also in this case we can find our point f of z. In order to be able to do this, we need some computability assumptions. So as I said, the general philosophy is that basic open sets are searchable. That means we want to have an assumption which does not give a new procedure or a much different procedure for different points, but it should be uniformly searchable. That means there is a computable enumerable set L, such that for every I in the domain of X, we have that the pair IN is in L exactly if Bn contains Xi. So in other words, we have again a program which first takes as input I, and then gives again a program that generates all the Bn that contain Xi. Moreover, we need a set that is not only dense with respect to the delta topology, but also with respect to the conjugate topology, so that we can define the topologies in a way which as we need it. And we need again that we can enumerate, if we have the quasi-metric delta, Q is a rational number, U is a dense point, and Xi is some computable point in the space, then we want to enumerate these triples in such that this the distance is lower Q, and we want to do the same for the conjugate metric. So this too, here I've written it in the way, so it should be delta star of Uxi, but I used the definition so that we have this way. And this is, look to the dagger, this is an important requirement. So one can now construct such an indexing X that satisfies these requirements. So we will have that Markov maps between effectively given quasi-metric spaces, that is spaces that have these computability requirements. So Markov maps between such spaces are effectively continuous. Then the question comes up, but we have seen that is not true because of Friedberg's operator. So let us look what happens. So Friedberg's operator is such that the range is only these two functions, either the functions which is always 0 or the function which is nowhere defined, that means the graph is the empty set. So this function is of course then a finite function, and in the topology with respect to the conjugate metric is such that this set is open. So there is a small rational number that there is a ball around this function which contains only this function. Now in the setting of Friedberg and also in usual computability theory, we deal with numberings of the partial computable functions which are such that the set of all programs that compute the nowhere defined function, that means that diverges for all, that does never hold for any for all inputs, that is pi 0, 1 complete, which means it is not enumerable. More or less this is what is known by the halting problem. That means with respect to this canonical indexings, you cannot enumerate programs such that, or pairs of program and input, so that you know the program holds for the given input. The problem now is that this property is not satisfied, this property, by this result. So that is with the settings that I described, or this one, with this setting, Friedberg's case is just outside the setting. So that means we can prove we have a general result on the effective continuity of Markov computable functions, but the kind of numberings that we have to use is such that it is not satisfied as in Friedberg's case. Sorry, no. We can do this, but then we have to use the halting problem as an oracle. So if we allow extra information, then we can that would be another possibility to rule out Friedberg's example. So what do we learn by this example? So from the earlier developments, the earlier examples that I presented, it seemed that the reason why there is no general result for the general positive result for the continuity problem seemed to be a topological one. Because when you remember to these pictures, so here we had, it was just the geometry of the basic open sets which allowed that you can find a witness. Here it was the geometry of the basic open sets that allowed you to find a witness. It was always that one thought, oh, there must be a topological reason that this result does not hold in general. But now we see we can have a general result, but nevertheless we have Friedberg's counterexample, and now the reason is a pure computability theoretic one, because we have seen that this condition dagger is not satisfied in the general result, and this is the reason that was a computability theoretic requirement, not a topological one. Okay, so that's what I wanted to tell you about the latest knowledge as far as I have obtained it on the continuity program. Thank you very much.
Thank you.